At the end of this lesson, the students should master solving the resultant of vectors using three methods: polygon method, parallelogram or triangular law, and using rectangular components. Students should also be able to resolve vector into its components. The resultant of vectors is the single equivalent force having the same effect as the original system of forces. Consider this particle acted upon by two forces. Due to these forces, this particle would move to a single direction. These two forces are equivalent to a single force called the resultant. Three methods may be used to determine the resultant. The first is the polygon method. In this method, we connect the tail of the second vector to the tip of the first vector. We get the resultant by connecting the tail of the first vector to the tip of the last vector. If we have three vectors A, B, and C, we connect the tail of B to the tip of A. Then we connect the tail of C to the tip of B. We get the resultant R by connecting the tail of A to the tip of the last vector, which is C. Using the parallelogram law, we draw a line that is parallel to A, passing through the tip of B, and a line that is parallel to B, passing through the tip of A. We get the resultant by drawing the diagonal of the parallelogram, passing through the tail of the two vectors. To compute the magnitude and direction of the resultant, we consider half of the parallelogram, which is a triangle. Generally, if two of the sides A and B are given, and an angle opposite to either of the known side, alpha, is known, we can use the sine law to solve for the third side, r. First, we solve for the angle beta by equating A over sine alpha to B over sine beta. After having solved for beta, we can solve for gamma by subtracting alpha and beta from 180. The third side is solved using the sine law. Now, if two sides and an angle between them are known, we can use the cosine law for the third side. If there are three or more vectors, we consider two vectors at a time. But now, let us consider these three vectors. We first draw a line that is parallel to A, passing through the tip of B, and a line that is parallel to B, passing through the tip of A. We get the resultant of A and B by drawing the diagonal of the parallelogram passing through the tail of the two vectors. For the resultant of A, B, and C, we draw a line that is parallel to C, passing through the tip of A plus B, and a line that is parallel to A plus B, passing through the tip of C. We get the resultant of A, B, and C by drawing the diagonal of the parallelogram passing through the tail of C and A plus B. This shows us that the three forces are equivalent to a single force R whose direction is theta. We can also get the resultant of vectors by resolving the vectors into their rectangular components, meaning we get the x and y components of the vectors. Consider vector f directed theta north of east. Its components about the x and y axis are f sub x and f sub y. Rearranging the vectors following the tip-to-tail method, we form a right triangle. For right triangles, we can use the trigonometric relations, such that the cosine of theta is equal to f sub x over f, and the sine of theta is equal to f sub y over f. Rearranging the equation, the x component of f, which is f sub x, is equal to f times cosine of theta, and the y component of f is equal to f times the sine of theta. Now suppose we are given the components and we are to get the magnitude and direction of the resultant. For a right triangle, we can use the Pythagorean theorem to solve the resultant f, which is equal to the square root of f sub x squared plus f sub y squared. The tangent of theta is equal to f sub y over f sub x, so that the direction theta is equal to the inverse of the tangent of the absolute value of f sub y over f sub x. If the given direction is with respect to the y-axis, the sine of phi is equal to f sub x over f, and the cosine of phi is equal to f sub y over f, so that the x component of f is equal to f times the sine of phi, and the y component of f is equal to f times the cosine of phi. If we are given the components f sub x and f sub y, the magnitude of f is equal to the square root of f sub x squared plus f sub y squared. Now the tangent of phi is equal to f sub x over f sub y, and the direction of f is equal to phi, which is equal to the tangent inverse of the absolute value of f sub x over f sub y. Using the rectangular method to solve the resultant of these three forces, we get the summation of the rectangular components of these three forces. Those are the summation of forces about the x-axis and the summation of forces about the y-axis. We follow the sign convention in the Cartesian coordinate system. X components that point to the right are positive, and those that point to the left are negative. Y components that point upward are positive, and those that point downward are negative. So for vector A, the x and y components are positive. For vector B, the x component points to the right and is therefore positive, while the y component points downward, thus it is negative. For vector C, x points to the left so that it is negative, and the y component points upward, thus it is positive. The summation of the x components is equal to negative r sub x, and the summation of the y components is equal to r sub y. Solving the resultant r, we use the Pythagorean theorem so that r is equal to the square root of the quantity negative r sub x squared plus r sub y squared. And the direction theta is equal to the tangent inverse of the absolute value of r sub y over negative r sub x. Since r sub x is negative and r sub y is positive, then the resultant is found in the second quadrant. The resultant is therefore directed theta north of west. If we are given a force vector and we are to resolve it to its components about two known axes, we can use the parallelogram law to obtain the components. Using the parallelogram method, we draw a line parallel to the a-axis and a line parallel to the b-axis, both passing through the tip of r. The component about the a-axis is from the tail of r to the intersection of the a-axis and the line parallel to the b-axis. And the component about the b-axis is from the tail of r to the intersection of the b-axis and the line parallel to the a-axis. So, the effect of a single force R is just equivalent to the action of the two forces A and B. Using rectangular components, we equate the x and y components of R to the sum of the respective x and y components of the forces about the A and B axis. The components about the A and B axis should envelope R as shown. The x component of the resultant R cosine theta, is equal to the x component of A plus the x component of B. Both are positive because they point to the right. The y component of the resultant R sine theta, is equal to the y component of A minus the y component of B. The unknowns A and B can be solved using these two equations. For the system of coplanar forces acting on the particle, what is the resultant of the three forces, and what are the components when the 800 Newton force is resolved along the U and V axis? For the first part of the problem, we are required to solve for the resultant. Using rectangular method, we get the summation of forces about the x-axis. For the 600 Newton force, the x component is negative 600 cosine 60. For the 800 Newton force, the x component is 800 cosine 70. For the 350 Newton force, the x component is 350 cosine 25. This is equal to the x component of the resultant, which is equal to 290.8238. Next, we get the summation of forces about the y-axis. Now we have 600 sine 60 plus 800 sine 70 plus 350 sine 25. This is equal to the y component of the resultant, which is equal to 1419.2857. Solving the magnitude of the resultant, we get the square root of r sub x squared plus r sub y squared. Plugging in the values, the magnitude of r is equal to 1448.7755 newtons. The direction theta is equal to the tangent inverse of the absolute value of r sub y over r sub x. Plugging in the value, theta is equal to 78.4199 degrees north of east. Since both r sub x and r sub y are positive, the resultant is found on the first quadrant. Therefore, the resultant is directed 78.4199 degrees north of east. For the second part of the problem, we are required to solve the components of the 800 Newton force about the U and V axis. The components about these two axes should envelope the 800 Newton force. Using rectangular components, we get the summation of forces about the x-axis. We equate the x components of the components about the U and V axis to the x component of the 800 Newton force, so that negative f sub u sine 20 plus f sub v sine 75 is equal to the x component of the 800 Newton force, which is 800 cosine 70. And for the y components, f sub u cosine 20 minus f sub v cosine 25 is equal to the y component of the 800 Newton force, which is 800 sine 70. Solving for f sub u and f sub v, we have f sub u equals 751.9 7541 newtons and F sub v is equal to 972.9033 newtons. For the next sample problem, if three forces act on a particle such that they create a resultant R, determine the following. A. The resultant of the two known forces P, the minimum resultant, and the corresponding magnitude of F. First, we are required to solve for P, which is the resultant of the 200 and 250 Newton forces. Using rectangular components, we get the summation of forces about the x-axis. For the x component of the 200 Newton force, we consider this triangle whose sides are 7 and 24 and whose hypotenuse is 25. To solve for the x component, we get the cosine of theta, which is equal to 24 over 25. So the x component of the 200 Newton force is negative 224 over 25. Negative because the arrow points to the left. For the 250 Newton force, the x component is 250 sine 40. This is equal to the x component of P, which is equal to negative 31.3031. For the summation of forces about the y-axis, the y component of the 200 Newton force is equal to 200 times 7 over 25. 7 over 25 comes from the sine of theta, which is equal to 7 over 25. Plus the y component of the 250 Newton force, which is 250 times the cosine of 40. This is equal to the y component of P, which is equal to 247.5111. Solving the magnitude of P, P is equal to 249.4827 newtons. Since the x component of P is negative and the y component of P is positive, P is found on the second quadrant. Therefore, P is directed 82.7920 degrees north of west. For the next part of the problem, we are to solve the minimum resultant and the corresponding value of F. Now that we have a value for P, we can replace the 200 Newton force and the 250 Newton force with P. Using polygon method to determine the minimum value of the resultant, we connect the tail of P to the tip of F. The resultant is obtained by connecting the tail of F to the tip of P. However, since the sense of F is just assumed, we also consider when F is directed south of east. Again, we could obtain the resultant by connecting the tail of P to the tip of F. Since the magnitude of F is variable, we could make it smaller. But R is still not minimized. We could make R perpendicular to P. However, only when R is perpendicular to F is it minimized. In general, the vector which we want to minimize should be perpendicular to the vector which has an unknown value. Consider this triangle where we could obtain the minimum resultant. From the given, F is directed 52 degrees south of east, and based from what we have solved earlier, P is directed 82.7920 degrees north of west. The other interior angle to the left of P can be solved by subtracting 82.7920 from 180. To solve for alpha, we subtract 97.2080, and 52 from 180, giving us alpha equals 30.7920 degrees. To solve for beta, beta is equal to 180 minus 90 minus alpha, which is 59.2080. Now we have three known angles and one known side. To solve for the minimum R and F, we can use the sine law. In this equation, we have two unknowns, and we can solve for the minimum R, which is equal to 127.7159 newtons, directed 38 degrees north of east, and F, which is equal to 214.3135 newtons, directed 52 degrees south of east.